All right, let's see. In terms of reminders, you have a mastering due tonight. We're almost done with masterings. There's mastering due tonight, 2 next week, then your exam, then 1 left. That's it. Then final. We'll do a group quiz on Friday, and your exam 3, which covers chapters 4 and 6, is November 21st. Yeah, counting down. What do we got left? All right. So, chapter 6 is about energy transfer, thermodynamics, heat, moving from one place to the other. So, when we talk about energy transfers, especially in general chemistry, we're talking about energy being the ability to do work, the capacity to do work. And work is the result of a force acting through some sort of distance. So if you have 2 billiard balls colliding on a table, that would be work being done, which results in an energy transfer. All right, so one ball is working on the other, which results in an energy transfer from one to the other. So that's a kinetic energy transfer, right? One ball was in motion and gave some of its energy to the other one. Another way to transfer energy we can also exchange energy using heat. So the flow of heat from warm to cold is an energy transfer. The warm substance is giving its energy to the cold one, so that they eventually become the same temperature. So that'd be an energy transfer between 2 objects, 2 molecules. So heat and work are the 2 main ways we're going to talk about transferring energy. Bless you. All right, heat and work. So thinking about types of energy, there are 4 big types of energy. 2 of these you're probably really familiar with. Probably everyone has heard of kinetic and, whoa, you guys all right over there? A lot of sneezing going on. All right, kinetic and potential are probably the ones that we are most familiar with, right? Kinetic energy is energy associated with motion And potential is energy associated with the position. But there's two other types of energy we're going to use in here. One is called thermal, and that's the energy associated with how warm or cold an object is. And chemical energy, which is energy associated with the electrons around the atom. How likely is those electrons to be transferred or received? That would be chemical energy. All right, so we're able to examine all these types of energy and make predictions about where the energy is going to flow to. So based on what we know about kinetic versus potential energy, and what we know about chemical or thermal energy, we can make a prediction about, oh, the energy is going to transfer from here to here, and oh, the ice cube will warm up, or the reaction will go forward because it has a change in chemical energy. So this chapter is going to be talking majority about how do we make predictions about energy transfers. How do we measure energy, and then how do we predict what's going to happen next. Is everybody caught up with that? Sorry, they accidentally double-sided my slides again, so I have to flip back and forth. All right, so here is our law, all right, conservation of energy. Which is probably, if you know nothing about chemistry, this is probably the one thing you remembered from middle school, right? The energy cannot be created or destroyed. Energy can only be transferred from one type of energy to another type of energy. We can't make any new energy. We can't use up energy. It's just transferred from one type to another type. So we could transfer energy, right? We could imagine having potential energy to kinetic energy, right? That's when you hold the ball above your head, it has potential energy, you drop it, and now it's kinetic energy. So you've changed the type of energy from one to another. You could also imagine a reaction that it had chemical potential, it had chemical energy, it had the ability to go forward and make a reaction, and then it did the reaction and the flask got hot. All right, so the reaction went forward and then your reaction got hot. You could do the other way, right? You could imagine that you heat your reaction and you force a chemical reaction to happen. So these are interchangeable. You could go chemical, thermal, thermal to chemical, either way. So to determine the type of energy and how much energy, is being transferred, we need to define the system being investigated. Right, so the only way we know if it has potential energy is we can say, oh, I'm specifically looking at the ball I'm holding above my head. That is what I'm looking at. I'm going to watch that ball fall. So that's the type of energy. So to determine the type of energy and how much energy is going to be transferred, we have to come up with some definitions, some parameters for this energy. So there's two big things we need to define. We need to define, what am I saying when I'm saying system? What do I mean? This is the part of the universe where the reaction is taking place. We're going to talk about the universe like in its enormous entirety. Because if energy in the entire universe cannot be created or destroyed, I'm looking at one specific little area of the universe for my reaction and seeing about its energy transfer. So the system is just a little tiny bit of the universe where a reaction is taking place. And then we have surroundings. Which is the part of the universe exchanging energy with the system. So it's a pair, right? There's the thing that's having this reaction happen, and then the surroundings is where the energy is going to, or where the energy is coming from. So they have to come as a pair. So systems and surroundings always go together. All right, so let's take a look in depth about what this system and surroundings are and how we can start to measure how much energy is out there. So if the total energy of the universe is a constant, and I can't create or destroy any new energy, I have to have a way of measuring how much energy a certain thing has. And so first we're going to talk about internal energy, then we'll talk about some of the other ways that energy can be measured. All right, internal energy, given the snazzy little IE symbol, is all of the kinetic and potential energies of everything in the system, right? Where the system is where I'm looking at the reaction taking place. And it is a state function. Where Chapter 4 was very mathematical and very forward-thinking, Chapter 6 is super theoretical. Not a lot of math, mostly big thoughts. So there's a little bit of both, so depending on which one you like better. All right, so a state function has a value that only depends on the initial and final state of the system. The key to a state function is that we look at its initial energy, we look at its final energy, and that's it. Doesn't matter how it got to its final energy. We just look at the initial energy and the final energy. So you could think about if you had your party balloon, right, from lab, you had that little tiny rubber balloon, the party balloon. I'm asking everybody in here, imagine, to blow up the party balloon, right? Some people are going to be able to blow it up on the first try, get it all the way inflated, tie it off. Other people are going to have to take a few attempts at it. Either they blow into it and didn't have enough breath, or you blow into it and you didn't quite tie it off right. Doesn't matter to me. I'm just asking you to initially have a flat balloon and the end have a blown up balloon. That's a state function. I don't care how many times it took you to do it, or if you had to do it a few different, doesn't matter how you did it. Just, I want to go from flat to inflated. So that would be a state function. Do I put this on this slide? I'll put it up here. All right, so this right here, initial and final states, what are those? I'll put it up here. So initial and final states are defined by either pressure, temperature, concentration, or phase. Right, so the balloon one is pressure. I'm just looking at the final pressure minus the initial pressure. Right, the balloon was inflated compared to deflated. Temperature, think about your ice cube in your soda. Right, the ice cube was cold, then it got warm. That's all I'm looking at in terms of temperature. Concentration, maybe it got diluted. Starting at concentration, go into, or phase, we could have been doing a precipitation reaction. Right, we go from aqueous all the way to solid. So changing phase in some way. So if internal energy is the sum of these energies, and we're looking at the initial and final state, there is definitely a way to mathematically calculate that change in internal energy. All right, so internal energy change. Does anyone know what this big triangle means? It means change in. Yep. So big triangle symbol. And it's usually defined final minus initial. Right, I'm saying final something minus initial something. So internal energy change is going to be the change in E for energy. And so if it means change in energy, it's going to be energy final minus the energy initial. Right? Whatever my final energy is minus my initial energy. All right, well let's look at this little picture first. All right, so let's say I have these two reactants. I have a carbon solid and an oxygen gas, and with my bare hands, I squish them together to make carbon dioxide. That's not exactly how it happens, but it could, right? Imaginary world, I could make some carbon dioxide. Which is of higher energy, the reactants or the products? If the energy is going from 0 to, we'll say 1,000, which one's higher energy? Which one's closer to 1,000? Right? The reactants are higher energy. And these guys are lower energy. So if I wanted to figure out the change in energy, let's make up an imaginary. Let's say this is at 800. My delta E is final, which is the product, minus my initial, which is my reactants. So I would have a negative energy value. Which seems weird, right? Negative energy. But really, the negative sign tells me the direction of energy flow. So it's not saying that the universe sucked energy away into a black hole. It's telling me which direction the energy went. In this case, I started off at high energy and I didn't need that much to make my final product. I had more energy than I needed. So it is telling me that, I'll even write this down. All right, so the question is, where did the energy go, right? If it's minus 800, where did it go? All right, so the reaction is the system. The system's where the reaction's taking place. All right, and so the system has a negative energy, so it's lost energy. And so since the system and the surroundings are always paired together, if the system has lost the energy, the surroundings must have gained the energy. Which is why I'm showing my snazzy picture here, right? This is my system. I just calculated that the E, in this case, right, it was, the system lost 800. But that must mean the surroundings has gained that, so the same amount. So it depends on who I'm looking at. If I'm looking at the system, it's a loss of energy. But if I'm looking at the surroundings, it's a gain of energy. Right? It hasn't gone missing. It just transferred from one spot to the other. So how do we go about quantifying how much energy that is? Oh, question, Justin. Mm-hmm.
So do we need to, like in the nitrogen chemistry and stuff, do we need to be specific with like the plus and minus?
Yes. Yep.
Even on the test? Or
If there's a minus or a plus, you have to have it there, because otherwise you don't tell me which direction it's going.
okay.
Oh. This way? Mm-hmm. All right, so we've had an exchange of energy now. It's gone from the systems to the surroundings. So how do we calculate how much energy that was? I'm sure you guys are all wondering, man, I really want to calculate how much energy that was specifically. Excellent question. So, let's see if I can get this up. There we go. All right, so the system can exchange energy with the surroundings through what we talked about like 10 minutes ago, heat and work, right? That's the only way we can transfer energy, heat and work. Work gets the snazzy symbol W. Heat is called Q. I don't know. Question first. Yeah.
Okay.
Ask away.
So, will the energy always go from the system?
No, it can go the other way.
Okay.
In this case, right, I had, going from reactants to products, I had more energy to start off with than I needed. And so we're going to talk about here in a second, the reaction would get hot, right? It has to give off that energy somehow. But in theory, my reactants could be low energy and my products be high energy, in which case it would get cold. Because I'd have to suck energy in to make it work.
So are the products like the surroundings? Like the reactants would come to the system losing the energy?
No, so reactants and products all together are the system.
Okay.
And then, like, the water is dissolved in, or the air around it would be the surroundings.
Okay.
Mm-hmm. All right, heat and work. So, work, W, heat, I don't know why, Q. I guess that, well, because we're going to use a different letter for H later on, so I guess they didn't want to confuse us. So, heat, that's the letter Q. All right, so since we have the first law of thermodynamics, that energy is never created or destroyed, we're just going to exchange it from one form to another. This change in internal energy, which we call delta E, and we only exchange energy through heat and work, this delta E must be directly related to this heat and work exchange. So the change in internal energy is the work done and the heat exchanged. So we can look at some, since the positive and negatives are a big deal. Let's zoom in on this guy. There's this little table, it's also in your textbook. But Q, if heat is a positive number, it means my reaction has gained thermal energy. It's gotten warmer. If my heat is negative, it means the system has given away its energy to the surroundings. That's telling me the direction it's going. If my work is a positive number, it means that I have done something to my reaction. If it's a negative number, it means that the work is done by the system onto the surroundings. It's done something to somebody else. So delta E, if it's positive, it means I'm putting energy into my reaction. If it's negative, like it was in the last one, it means that the energy is going out of the system into the surroundings. So they're all kind of related to each other. So to think about how that works in real life, we'll play some pool, imaginary pool. You see those numbers? Sort of. I'll rewrite them up here. All right, so I have my cue ball, right, that I've just struck. So now it has kinetic energy. It's flying across the table. It is a smooth table, but it's going to lose some energy to friction, right? So that would be heat, gives off some heat. And I lose half a joule. So I start off at 5. If I lose some to the table, means I have this 4.5 joules of energy to hit the other ball with. All right, that makes sense. So this heat, right, we give the letter Q. And if it's heat lost, it's telling me the direction must be negative because I'm going to the table. The heat was on the ball, it's giving it away to the table. And if I start off at 4.5, I end up at, or I start off at 5, I end up at 4.5. The work is also a negative number, right, because I'm doing work on the other ball. If my cue ball is the system, at the end, it gives it away to the surroundings, which is the other ball. So it must be a loss of 4.5. So overall, my delta E, right, because I've given the energy, all the energy was in this cue ball, and at the end, the cue ball has given away all its energy, and the other ball has all the energy. So this is minus 5, but now this ball has gained 5. All right, so no loss of energy, it's just gone from one ball to the other. Now imagine you're playing at probably the pool tables that are downstairs at Craner. They have like little ridges in them, not quite so smooth anymore. Probably a little divot in it where someone had their cue stick and like dug up the felt a little bit. Same thing, I'm going to start off this ball with 5 joules of energy. But now, the table's super rough. So it's a negative 3 joules of energy. So how many joules of energy do I have left to hit this ball with? 2. So same thing, I'm still going to start off with 5, but now more of the energy has gone to heat, so I have less energy to hit the other ball with. They still end up with 5 overall. So my W is now 2, where before my work energy was 4.5. So they still add together, right? Overall, the energy still adds up to 5. It's just a different amount of Q and W. One has less heat, one has more heat. So if it has more heat, it has less work. So it's just a trade-off. Yes, question?
So does it matter that you're adding like positive and negative numbers?
No, just the overall. Oh, because it's state function. Because the state function, I start off with 5 and I end up with 0. I start off with 5 and I end up with 0. Doesn't matter the amount of Q and W, as long as they come together to be 5. The negatives are going to be confusing. It just tells me who's getting the energy. So, right, in this case, it goes from 5 down to 0, but it means that this guy went from 0 up to 5. It's just telling me who owns the energy right then. Still confusing? Okay. All right, so now we would like to move from theoretical to more calculations. So how do we quantify how much energy and heat? All right, so heat, right, is an exchange of thermal energy between a system and the surroundings. How do we typically measure, what units is heat, thermal energy usually measured in? I would say either degrees Celsius or Kelvin, depending on what you're specifically looking at, right? Temperature. All right, so thermal energy is going to always flow from a high temperature to a low temperature. All right, so if you have a high temperature something, it means that those molecules in there, remember like our gas discussion, right? The higher the temperature, the more speedy the molecules are, the more energy they have to collide with other things. As they collide with cold things, they're going to give away some of their energy. And so the cold things get warmer, and the warm thing gets colder, and eventually they kind of meet in the middle. So if you think about, right, you put your ice cubes in a drink. The idea is that the drink is warm and has lots of energy, and the ice cubes don't have much energy. So the drink is giving its energy to the ice cubes, and eventually the ice cubes melt. And the drink should be colder, because it's giving away a lot of its energy. Next time you have a drink with ice at lunch, think about that. Be like, look at that, thermodynamics at work. You can talk about it with your friends at your table. Be like, hey, see what's happening right there in your cup? Let's talk about heat flow. You may have other things to talk about at lunch, but if you don't, you got some time to kill. That would be a good conversation starter. All right, so if that is heat, and heat is going to flow from high to low, I'm looking at right, change in T, change in temperature. So if we look at the change in temperature, we can learn some stuff about heat. Where's the heat going? How much do they have to start off with? All right, so we're going to measure heat. We're going to look at its change in temperature. When a system or a reaction, absorbs heat, its temperature has to change. That makes sense, right? I mean, if I'm putting heat into it, I'm taking heat away from it, the temperature has to change in some sort of way. If I'm saying absorbed, which way is it going? Is it going into the reaction, or is the reaction giving it away? It's going into the reaction. So I'm saying absorbing. I'm saying the heat is going into the reaction in some sort of way. And so the heat absorbed is actually proportional to delta T. Through this equation. All right, so this is Q, like I've used before. That's heat. There's a change in temperature, specifically in degrees Celsius. Then we have a new letter. C, big C. Big C stands for heat capacity.
So that's multiplied by,
Yeah, you can put like a little dot or something. I say I'll put an X in there because then it looks like an extra variable. It's just C times delta T. All right, so heat capacity is this. It's the amount of heat required to raise the temperature by 1 degree Celsius. So temperature of whatever, right? Temperature of water by 1 degree Celsius, or temperature of iron by 1 degree Celsius. It's how much energy, or how much heat, which is a measure of energy. Right, and joules is our units of energy. So it's how many joules per degree Celsius is required to heat something up. All right, so we have that equation. Heat capacity is going to depend on how much you have, right? Amount of matter. So how much heat is required to raise the temperature of the ocean by 1 degree Celsius is going to be very different than how much energy is required to heat my coffee mug by 1 degree Celsius, right? So those are two different quantities that require different amounts of energy. We can get around that by using this thing called the specific heat capacity. So specific heat capacity is the quantity of heat required to raise the temperature of 1 gram of material by 1 degree Celsius. So specific heat capacity is given the symbol C little s. So it's the same heat capacity, but now the little s tells you it's the specific heat capacity. So its equation, all right, so this is the heat capacity equation. Looks very similar, but now I have heat, change in temperature. My specific heat capacity, and any guesses on what M is? Mass. It is mass. What units should mass have? Based on this guy up here. Grams. So the difference is if I have the overall heat capacity, I'm looking at who knows how much. But if I use the specific heat capacity, I'm looking at a specific amount of matter. Hopefully they'll remember which one is which. The unit should also give it away, right? This one is in joules per degree Celsius, so who knows how much. But this is in joules per gram degree Celsius, so you'd have to know something about the grams to make those units cancel out. All right, so specific heat capacities are super useful, and they tell us all kinds of fascinating things. So this is also from your table. You'll need this from your homework next week. But specific heat capacities of different elements and compounds. Which thing on here has the largest specific heat capacity? Water. That's why water is amazing on a bunch of different levels. It takes, if you compare water to even just ethanol, which are very similar, it takes twice as much energy to heat up a gram of water compared to a gram of ethanol. Or if we look at water compared to just about anything else, gold, right? It takes 40 times as much energy to heat up water compared to melting gold. Craziness. Which is why water is just amazing. It absorbs all that heat and it doesn't really get all that hot, right? Because if it got hot really easily, our oceans would be boiling all the time. And they're not. They're able to maintain their temperature because they're able to absorb tons and tons of energy and not change temperature. Again, which is why it takes you forever to boil a pot of water. You got to put in a ton of energy to get your water to start to boil. Especially if you're sitting there watching it, it seems like an eternity. But that's why water is just fascinating. Otherwise, you would be internally boiling all the time, right? Because you're at, fairly warm on the inside. If you were filled with ethanol, your veins would be boiling all the time. Just think about it. It's just, Again, another fascinating thing to talk about at lunch. Like, do you know a lot about water? Justin.
Down on the material part.
Yeah.
Like with glass,
Mm-hmm.
sand.
Yep.
You can make glass from sand.
Mm-hmm.
Why does sand take more?
Because sand is individual particles, they're not connected to each other, right? Sand particles, but glass has cross-linked. So now if this one gets warm, it transfers its energy across to the next glass molecule. And so it's a little bit less heat. But again, this is why glass is a really good insulator. Not great, but good. In that it takes more energy than it does, some of these metals. And so a metal heats up really fast, like a copper pot heats really quickly, but it doesn't maintain its energy for very long. But a glass cooking dish takes a while for it to get warm, but once it is warm, it stays warm for a really, really long time. So that's fun cooking facts. Why we don't use copper cookie sheets, because they would not maintain their energy very long once they got warm. So they would burn on the bottom and not transfer their heat to the cookie. You end up with like black bottoms and squishy tops, which maybe that's how you like your cookie, burnt on the bottom and raw on top. But at that point, you might just eat the raw cookie dough, to be honest. All right, let me do one last thing. Actually, let me do this. Let's do one example using our brand new equation. And that'll be our last thing for today. Using our specific heat capacities. All right, so how much heat does gold absorb if you have 2 grams of it and it starts off at room temperature and you warm it up to 100 degrees Celsius? All right, so of all these variables, which one am I looking for? If I'm looking for heat, which variable is that? Q, right, I'm looking for Q. So what is the M in this equation? 2. And then CS, I would go over here to the table. 0.128 joules per gram degree Celsius. And then what would delta T be for this? 75. I just made this up off the top of my head, so I have no idea what the answer is.
So you just, that's just, with that chemistry part, you just have to figure out the difference.
Yeah, it's just the difference. It's, in this case, it's a positive temperature change because I was at 25 and I got hotter. It could, in theory, start off at 100 and get colder, and then we talk about how much energy was released. 2 times 0.128 times 75. What would be my units of this? Joules. All right, we will do more with that on Friday. I have your quizzes to get back to you. They're, of course, in